every other app in the App Store. How do they resolve that? Also, they talk about warming up, right? Does that mean the warming up is for the new apps that come in the store?
So they do talk about the serving part. They do talk about that problem specifically. So what they do is they prefetch a number of examples using some algorithm, which I can't remember what it was.
Oh, okay.
But they prefetch some examples and then apply the recommender system on the ones that have been prefetched. And they make a recommendation based on that subsample of the data, so to speak. The other question about the warm-up is because they are updating the model live. So what they have is they have the previously state-of-the-art model, so to speak. They use that to warm start the new models, and then they retrain the new models. If the new model works, this new model becomes the warm-up model. Otherwise, they discard it and they keep the previous model.
And just thinking about like recommendation systems, like in that setting, because like the 101 recommender system is collaborative filtering, right? How is that is it just taking that idea because you, through this aggregation of all the users, you kind of, the network sort of pick out like your similar users or whatever. Do you think these two ideas, I'm just wondering how different are these two ideas in general?
Not sure. I mean, does anyone want to comment on it?
Yeah, just wondering like if there's any comment on this.
Yeah.
And also like coming back to the neural network, like generalized. I'm just wondering like how does it actually generalize? Because if you have like a small sample of data and small sample user actions, you're bound to overfit, right? Like to certain actions.
Yeah, but they don't have a small sample.
So provided that you have a big user pool of everyone and then prefetch that list of recommender system, this would happen, and then you can generalize. Because it's just turning to memorization into one and zeros. It would not recommend 1 zeros, but because it pass through a sigmoid, everything will be like between 0 and 1. So like
that's how they rank them, right?
Into soft labels.
Yeah, well, so the generalization part, I think a couple of weeks ago we presented a paper where they explained this theorem about what needs to be satisfied for generalization, and there are two conditions there. I can't recall them just now, but it's learnability and guaranteeing that there's a local maximum, something like that. So neural networks fit that description, so you can be sure that a dense network is going to generalize. That about generalization. The part about memorization, well, it's just sometimes you want the model to overfit the data, so it continues giving you the same predictions that you had before. Yeah. Yes.
So if I remember from the paper, there was mention that the wide part that's able to do the memorization is important for capturing like really niche interests.
Yep.
So presumably people that are like rating apps that in the combinations that other people don't rate, or presumably they rate them strongly, and there's just not that many of those groups, so they're like a niche interest group. Would you be able to see that reflected in the wine set? I mean, presumably, or is the way that you have the wine set means that would be, would you see that phenomenon?
Maybe if we include more features, maybe yes, and if we train only the wide models. So that what you just said is the definition of overfitting. So the model sees a set of inputs and it always gives the same output.
Yeah.
So when it sees a combination of 2 or 3 features, it ignores the rest and then it gives a single output all the time. It is always possible to make a model overfit. I think it was said once that if you can't make a model overfit, don't even bother training it for learning. So yeah, overfitting is well known. You can do it with almost any data set that you have.
I guess I thought I meant that you want to also reflect the interests of niche users as well as the kind of the more.
Yeah, so that is the intuition behind the model. If that is what the network is actually doing, is I would say an open question. But it is the intuition behind the model is that you have one side that is overfitting, so it is capturing these niche interests, so to speak, and you have another part which is more generalizing and looking into the combinations of all the features. And then you have one last output neuron. So that last output neuron is supposed to be discerning, do I have to recommend the niche interest or do I have to recommend the generalizable interest? So there you get a number between 0 and 1, and that's how you rank your outputs for recommendations.
So I was curious partly because with regard to the wine data set, if it's all professional wine critics, you might argue that they're going to agree with each other because they're all very skilled and they know what's good wine.
Yeah, maybe. That's an interesting exploration question. If you want to explore it, download the code. It is so the data is loaded with pandas, so it is fairly simple to add new features. So if you want to include the wine taster into the mix, what you have to do is make the wine taster, make a vocabulary of wine tasters, and then make embeddings for the wine tasters. So for the white part, you can include one hot encoding, so you can concatenate one hot encoding of tasters, and I can't remember how many tasters there are, but whatever many. And for the deep part, you can make an embedding of taster and see what happens. Should be interesting.
Yes. What's the relative performance between the linear model and the deep model? And if you separated them out and ran the same experiments?
Yeah, so that's what they report here. I didn't do it myself, but they report it here. So you have, if you use the deep model, you do get a gain of about 3%.
I'm talking about the null case. Did you separate out the model yourself in your code? In
the wine data set? No, I didn't separate them. But again, using the sequential, the Keras sequential interface is very easy to create. It's very easy to do that. So, I'm being serious. If any of you wants to try this, download the code, copy and paste here and there. So if you wanted to try that, so if you do just input and then dense. So you do the input and dense, then you have your linear regression model. And if you just do input and then all the rest without concatenating, you have the deep part. So it is very simple to separate both models and combine model, train them with the same parameters on the same data, and see what is how they compare. We might find that we get the same performance with only the deep model, for example. Maybe that would be interesting.
Yeah, I mean, the internal weighting would be very small, or vice versa.
Yeah. There's also one thing that I did not implement here, which is there's supposed to be a weight component here between both. There are several things that I did not implement here for the demonstration, but each of these is supposed to be weighted with a learnable weight, so it understands which part is more important. Looking at that weight alone might answer your question of which model is more important. And then you can also optimize each one with a different optimizer. That is a whole different issue. I wouldn't go too deep into that. Cool. Anything else?
I'm intrigued by the difference between online and offline, and the explanation they give. I mean,
it's very.
I find it a bit flaky. Anyway, just like I don't really understand what.